In our study of electrochemistry, the Board of Studies mandates that you examine 3 cells in detail. 2 of them are compulsory, that's the dry cell and then the lead-acid battery, and one's an option, and we've chosen to study the lithium cell as our option. But we start with the dry cell, or the Leclanché cell, depending on your French pronunciation. The dry cell was first proposed in 1866. It then became the most common cell, often just referred to as a AA battery. It's very cheap and it's able to produce a constant 1.5 voltage, which then gave rise to any number of devices like torches, calculators, and handheld radios, things that soon were developed to utilise this portable power after the development of this very cheap and stable cell. Let's have a look though at the chemistry of the cell, because that is what the Board of Studies requires that you understand. The first thing we need to understand is the redox nature of all cells. Redox is always happening, so we must be able to identify both the anode and the cathode and the equations that relate to these electrode reactions. So let's examine the anode of the dry cell. The anode of the dry cell is a zinc metal that oxidizes. You're familiar in seeing that zinc has a relatively high reactivity, which means that it loses electrons quite readily. It will oxidize spontaneously in air. It's not a violent oxidation, but it happens steadily as it loses electrons and forms zinc oxide. So it's a good, cheap, readily available product to use as an anode. Therefore, the whole battery, the outer casing, is actually made of zinc. And with some insulating seals that you can see highlighted in pink, bottom right of screen, the zinc casing is surrounding the entire cell, which makes it robust and sealed. And then the flat bottom that you're used to seeing on all these AA batteries is the site of the anodic reaction. Now, the anode reaction there is on the screen. You see that zinc solid oxidizes by losing 2 electrons and forming a zinc ion, 2+. That zinc ion will steadily increase in concentration as the battery discharges and powers the electrical device that it's plugged into. So you need to remember that an oxidation reaction occurs at the anode. Therefore, zinc is the anode as it's the site of electrons being sourced for this particular cell. We move on then to have a look at the cathode. Now, the cathode looks a little bit more complex, but again, we're interested in the metal of the cathode, which happens to be, at this stage, an ion of manganese in the form of manganese oxide. Now, this is a crushed up powder that's inside the cell. If you look at the bottom right of screen again, you'll see that manganese oxide is inside the cell. It's highlighted in that light green in the presence of some carbon and also some ammonium chloride, which is a salt or a paste. Now, what happens is that the manganese oxide is reduced to manganese hydroxide. More succinctly, the bigger equation underneath that first one shows that ammonium ions are being discharged to ammonia. You've got water, so it's not really a dry cell, but there's a very low concentration of water in the whole setup, so we do call it the dry cell. So the water and the ammonium ions are also reacting, but the main focal point of the cathodic reaction is what happens to manganese oxide when we introduce an electron. Manganese oxide is becoming manganese hydroxide. However, it's not immediately clear how this is reduction, so let's take a closer look at that process. Here's your cathodic reaction again, and I want to draw attention to the manganese ion. The manganese ion here has a 4+ valence or oxidation state. How do we know this? Well, there are 2 oxygens bonded ionically to the manganese metal. Now, oxygen being in group 6 will always have a valency of 2-. Now, if I've got 2 lots of 2-, the charge that the oxygens bring to this ionic compound is 4-. Manganese, therefore, here must be 4+ because the overall compound is neutral. It's not an ion. Can you see how it is neutral? MnO2 without a charge. Therefore, manganese must be contributing 4+ to the compound. On the right-hand side, manganese hydroxide shows that the manganese metal has been reduced from 4+ to 3+. How do we know this? Well, the key is examining the hydroxyl group. Hydroxide is the ion of hydroxyl, and the hydroxide ion has a charge of 1-. Because there are 3 there, we know that we are 3 negative in the compound for hydroxides. Therefore, manganese, because of the neutrality of this ionic compound, must contribute 3 plus. Therefore, the electron on the left has reduced the oxidation state of manganese from 4 plus to 3 plus. Therefore, reduction has taken place at the cathode, which is what we're used to seeing. Additionally, NH4 plus ammonium ions are discharged. This means that they are losing a proton or a hydrogen, and that hydrogen contributes to the formation of hydroxide from water. Now, chloride ions are spectators. If you look down the bottom right of screen, you'll see that the ammonium chloride paste has some chloride ions present. These chloride ions do not change their oxidation state. All they do is they provide a compound for the ammonium to be readily available when the cell is charged and ready for use. After the ammonium ions become neutral, they have no more electrostatic attraction to the chloride ions, but the zinc ions do, that are the product of the anodic reaction, and therefore zinc chloride is formed as a final product. So as this cell steadily gives up electrons to an external circuit and becomes flat, we'll find that zinc chloride steadily builds up in concentration until the point where the cell no longer functions. So at the start of this reacting process, there is no zinc chloride present at all, but as the cell starts to be discharged overall, more and more zinc chloride will be produced. Let's have a closer look again at the cathodic reaction to make sure that we can understand what's happening. We need to know that the reduction of manganese 4 plus is this cathodic reaction. You need to identify that. We also need to understand, however, that as is highlighted in green on the bottom right of screen, that the manganese oxide powder inside the cell is not the electrode itself. We use a graphite electrode. Remember, graphite from year 11 is an electrical conductor. It has a similar setup to metals whereby there is a delocalized sea of electrons that can move from one electrode to another. Now, a graphite rod is quite cheap to produce, and therefore this is the site of reduction whereby electrons that originated with zinc when it was oxidized return to the cathode from the external circuit. They run down the graphite rod inside the paste where manganese oxide is present, and those electrons then move from the graphite rod and reduce manganese oxide to manganese hydroxide. In this way, electrons move through the graphite electrode to reduce the manganese ion. Well, that's the chemistry of the cell, but how is this cell important and why do we study it? Firstly, it's cheap. It's the cheapest commercial cell. These days you can go and buy a 12 or 18 pack of Duracells or Energizers or Vartas from Bunnings, and you might only pay $9 or $10 for any number of these cells. They are very cheap and they produce a steady current and are most suitable for use in small appliances. They're small and lightweight, which means that they are very practical. It's not hard to carry these cells around with us and use them in our everyday life. The 1.5 volts is an adequate voltage for many of these low-powered devices, and it's enough to run a torch, as I said, clocks, toys. It's essentially a good source of portable power. The other thing is that they are quite robust and easy to use. We learned from a very early age how to plug cells into a toy, and their robustness comes about from the solid zinc casing that it's made out of. So they're very practical. How has it changed society? Well, they've revolutionised the way that electronics function. There was previously a limitation to electronic devices in that they needed to be plugged into an external power source like the electrical grid. But with the generation of these batteries and their development to common usage, we've been able to have undreamed of portability with small electronic devices. We also have seen that the concept of the dry cell became the stepping stone to the portable digital age that we now live in, where we rely on lithium cells, and we will examine that more readily later in the video. But for now, we need to understand that the concept of the dry cell from the 19th century was the first step toward the very portable power we have now in our lithium cells. What are the limitations of the cell? Well, firstly, it can't deliver very high currents. It produces 1.5 volts, but the magnitude of the power that it produces is not particularly high. Secondly, there's a relatively small amount of electricity that's able to be produced for the size of the cell. A comparative lithium cell, we'll see, can generate a far greater voltage and a much higher current for a battery that weighs far less. So though it was a good stepping stone, it has certainly been superseded in today's technological age. The other issue is that obviously if the anode is made of zinc and zinc is oxidizing, then zinc is disintegrating. So the cell itself will steadily disintegrate, and this can cause older cells to leak, and as they steadily oxidize, there are going to be issues with the breakdown of the seals, and therefore the cell will cease to function. What's the environmental impact of the use of these cells? Well, overall, it's quite positive. They have a small impact on the environment thus far. Both the zinc and the manganese metals are not particularly harmful to the environment. They're quite abundant, relatively easy to isolate and use, and they're quite cheap to produce. So there's no real issue with those starting reactants in those reactions. The finishing products of manganese hydroxide, over time, that was reduced to Mn3+. That will reoxidize back to a steady state Mn4+ in manganese oxide, which is a harmless ionic compound. Likewise, the zinc ions that are produced are harmless. In fact, zinc is a trace element that organisms need for survival in very small amounts. So at this point, there's no real danger from the disposal of these cells with regards to the zinc and the manganese. Likewise, the ammonium salt that is present, ammonium chloride, and the carbon, of course, is a harmless substance. So overall, there's no issue with chemical contamination from the disposal of these cells. But of course, whenever anything is disposed of in the environment that is non-biodegradable, like metals, we're potentially going to have landfill issues as more and more are steadily added to the disposal units as more and more are produced over time. The second cell we need to examine is called the lead-acid cell. Now, the lead-acid cell is essentially a car battery. It's actually 6 cells joined together in what's called series, which harnesses multiple cells' power to give an overall voltage that's much greater than a single cell, so that we get 6 lots of 2 volt to produce 12 volts in your car. The advantage of the lead-acid cell is that it's rechargeable. Let's take a look now at the chemistry. Firstly, we need to look at the anode. Now, the anode in the lead-acid cell is the lead plate. Now, we have many of these plates in the cell. If you look at that schematic representation down the bottom right of screen, you'll see that you have black plates. These have a large surface area and they're submerged in sulfuric acid. And there are many of these plates in each individual cell that are submerged in the acid and form the basis of the anodic reaction, which of course is oxidation. And so the oxidation reaction is essentially lead solid becomes lead 2+ ions and releases 2 electrons into the external circuit. But there is a bit more to it. I mentioned that the lead anodes are submerged in 6 molar sulfuric acid, relatively concentrated, strong acid, sulfuric acid, which means that this is the electrolyte. Sulfuric acid in solution forms hydrogen ions and the sulfate ion. So there we have charged particles in solution, which is the definition of an electrolyte. So this acts as the salt bridge, which enables the movement of ions and achieves overall cell neutrality. So when the lead oxidizes to lead 2+, it's now electrostatically charged, which means that it's attracted to the sulfate 2- ions, which are in solution from sulfuric acid. So the sulfate joins the lead and forms a new insoluble coating on that anode called lead sulfate. So as this battery does its work, we're going to find that lead sulfate will slowly build up on the anode. Lead sulfate is a product which will slowly flatten the battery as it builds up on the anode and reduces the anode's ability to further oxidize. The use of that word reducing there was not the best use of the word. I didn't mean that it reduced the anode, but what it does is it minimizes the ability of the anode to do its oxidation work. So the complete reaction at the anode then is that lead solid, in the presence of sulfuric acid, will actually produce lead sulfate, liberating 2 hydrogen ions and 2 electrons. How has lead been oxidized? Well, you need to be able to recognize that within lead sulfate, lead must be an ion 2+, and that's where the 2 electrons came from. But what about the cathode? Well, let's take a look at the cathode. The cathode is actually lead oxide, very similar to the manganese oxide that we looked at in the dry cell. Now, the lead oxide is also a plate. It's in a solid state, and again, they're the alternating pink plates in the diagram down below. They're also submerged in sulfuric acid, and they are the site of reduction. Like in the dry cell, we'll see that the reduction is a little bit more complex at first glance. Notice as well at this point that the lead atom in lead oxide has a oxidation state of 4+. We know that lead displays variable valency and can be readily reduced from 4+ to 2+, which in fact is exactly what happens. Let's take a look now. The anode reaction, well, it was this. We generated 2 electrons when lead became a lead ion and formed solid lead sulfate. Both of these electrons and those 2 protons, H+, are then used at the cathode. Let's take a look. The cathode is lead oxide, see it on the left. It's added to sulfuric acid in the presence of the 2 hydrogen ions and 2 electrons that came from the anode, and it forms lead sulfate and 2 water molecules. It's fairly straightforward. We can see that lead 4+ has become lead 2+. Therefore, the lead metal has been reduced. Once that reduction takes place, the car starts. So when we look at an image like this from your textbook, it's easy to see that the anode is the negative electrode, which is lead solid. The cathode is the positive electrode, which is lead oxide solid. There are 6 cells in series, each contributing 2 volts each. 6 lots of 2 means that 12 volts total can be produced by this battery. Remember that a battery, by definition, is a collection of cells. So each individual 2-volt setup of anode and cathode is called a cell, but the overall collection of 6 of them is called a battery. Well, how practical is it? Well, it's very practical. It's a rechargeable battery, so it means it's got a very long life, up to 5 years. It revolutionised the transport industry. It's done away with the crank arms that were used to turn over the starter engine in vehicles. Very cheap to produce because lead's abundant and quite cheap to extract. Sulfuric acid is one of the most commonly produced chemical products around the world. It's quite cheap to produce. The plastic housing and casing is sourced from crude oil, which is not great, but it's very cheap at this stage and quite robust and a good housing for these cells. It's quite serviceable too, which means that if you have a shorting out of the battery, you may not need to replace it. You can probably get it serviced. The impact on society means that it gave rise to long-haul freight and car trips that were now possible as the battery continually recharges when the car is in motion. It means that the efficiency of the engines were improved and electrical circuitry was possible, whereby things like central locking, power windows, stereos can still work when the engine is turned off as we draw on the battery power itself. By setting the cells in a series of 6, you can get 12 volts of power, which was previously unthought of when we had only the 1.5 volts available from the dry cell. As mentioned, you can recharge this battery, and you've seen the YouTube video that describes that, but all that happens is that when the car is in motion, the overall power that's being generated by the combustion reaction can be harnessed somewhat by an alternator, which reverses the poles on this battery and forces the reactions that have happened to the generation of power to reverse, and therefore lead is reformed in the place of lead sulfate, and lead oxide takes the place of the lead sulfate on the other electrode, and therefore these reactions are reversed. Environmentally, there's some concern with the use of this battery. Firstly, this is your favourite sentence. You know that lead is a bioaccumulative neurotoxin. and the buildup of lead can inhibit central nervous system function in adults, and when accumulating in unborn babies, in the fetus, mental retardation can be the outcome in severe cases. So lead anywhere in the environment is bad news for living organisms. The disposal of these batteries, therefore, is an issue for landfill, and they ought not to be disposed in landfill because there's a risk of leaching into the environment. Likewise, the sulfuric acid is a strong and concentrated acid that's highly corrosive. If that's leached into waterways after disposal, the pH can be lowered, which can have drastic effects on soil pH and water-dwelling organisms. So again, the sulfuric acid electrolyte must be monitored during disposal. However, because they have such a long life, the impact of their disposal is minimised because there isn't an endless dumping of batteries. For example, let's say they only lasted a month, that would be far worse. So the long life and the rechargeability of the battery minimises the environmental impact. One of the issues as well, though, is that the high currents delivered between the plates can cause the casing to buckle. It's only plastic, and as you know, plastic is affected by heat. And so therefore, if you have a lot of current, you can have a lot of excess heat, which can cause the breakdown of that plastic prematurely. If this happens, leaking acid can be an issue as it's corrosive, and it can also cause skin and eye burns. We move lastly to our study of the lithium cell. This is one that we've chosen to study, that you must choose. And so this lithium cell is a good choice for us because it's currently the best kind of battery that we have. It's usually just called a lithium battery. In fact, it's a cell because it's just a single cell, but it's often referred to as a battery. The one that we're looking at is called the lithium manganese dioxide cell, which was the earliest type of lithium cell. And really, the thing about the lithium cell is that it produces unrivaled power for its size, and we'll look at why that's the case. Firstly, the chemistry. The anodic reaction is very straightforward. You have the lithium metal oxidizing to form lithium ions, and the generation of an electron that will then go into the external circuitry to power the device. Interesting difference here is that the lithium does not become an aqueous ion. The lithium goes into solution, note the brackets. The reason for this is as follows. You know that lithium is highly reactive. It explodes in water and oxidizes very quickly in air, so you cannot put the lithium into a situation where there is water available. So when lithium oxidizes in this battery, it must do so in the absence of air and water. And the chemistry associated with the oxidation of lithium in lithium cells is such that the paste, or the solution that the lithium is inside the cell, is a hydrocarbon-based organic solvent. And this is the place for the electrolyte. Let's take a look at this schematic diagram from your textbook. At the anode then, we'll see that lithium, yellow on the screen, oxidizes to lithium 1+. And this lithium ion moves into the middle, there it is, of the cell. It's coloured pink. Where an electrolyte is, that's your organic solvent with a dissolved lithium salt. Now, a lithium salt, of course, will be a compound with a lithium 1+ ion and a negative ion, like a chloride ion or a sulfate ion or something similar. You don't need to know the details of the salt. So lithium oxidizes. At this point, we need to examine the anode. The anode, of course, being lithium, needs a closer examination to see what happens to the electron. You see that the electron exits the cell to the left. Once it exits the cell, it moves through the device and it will return to the cathode. It's ready then to do some work. So watch the movement now of the electron. The electron will move from the anode through the circuitry. Here I'm saying it's going to power a little light, on it comes, over towards the cathode, makes contact with a conducting iron lid, moves through the conductor at the cathode into the presence of manganese oxide. We're used to seeing manganese oxide now, and we're used to seeing that manganese oxide can be reduced. Note that the iron doesn't reduce, it moves through the cheap iron cap, which is simply a conductor that's insulated against the anode, allowing electrons to move down to the manganese to reduce it. Now here's the cathodic reaction. Manganese oxide on the left plus an electron in the presence of a lithium ion forms this compound on the right, lithium manganese oxide. At first glance, we should ask ourselves a question: how is that possible? But if we look more closely, we need to look at the oxidation state of manganese at the cathode before the electron arrives. It's 4+ to balance the 4- of the two oxygens. On the right, in lithium manganese oxide, it's become 3+. Why is this? Well, when oxidation occurs and the lithium ion is available from the salt, the manganese receives that electron, it's reduced to 3+, but the two negative oxygen oxides that each bring 2- to the compound, contributing 4-, stay attached to the manganese 3+. So 4- and 3+ are not neutral. There's an extra minus. You can see at bottom of screen. Therefore, the lithium ion in the salt in the pink section of the schematic diagram is now electrostatically attracted to the manganese oxide. Therefore, you now have a new compound. MnO2- is negatively charged, and the Li+ that was produced from oxidation moves through the electrolyte and forms the new compound, lithium manganese oxide, with the manganese ion 3+. Sounds complex, but these are the two half equations you simply need to know. Oxidation, lithium, forms lithium ions in an organic solvent plus an electron, and manganese oxide is reduced to lithium manganese oxide as the oxidation state of manganese goes from 4+ to 3+. Now, this reaction is capable of producing 3 volts of power, and this means that there are more electrons produced per gram of lithium than any other metal, which means it's the best cell we have to date. Now, the cost and practicality of this particular cell is very, very positive. It's exceedingly low weight due to the very low molar mass of lithium, generates more electrons per gram than any other metal, as I mentioned. It's therefore a very powerful and lightweight battery. Therefore, small cells are capable of powering fairly big devices. Button cells are a lithium manganese oxide cell, like in pacemakers and watches. AA or AAAs are possible for cameras, watches, calculators, iPods, etc. And a very high voltage is possible with a steady current that's long-lasting and are rechargeable. The impact on society then has been huge. The portable device age that we live in of cameras and iPods and iPhones and laptops and iPads has really come about because of the generation of power possible in lithium cells. Their long-lasting compact nature and the different shapes that you can make out of the cells means that they're very versatile, very robust, and used in all kinds of devices. They have a long life, which minimises the impact on the environment. Additionally, the lithium salts are very harmless, easily discarded. Manganese, we know, is harmless and actually a trace element for many organisms. But the disposal of any metal in landfill is to be monitored, because the more we dispose, the higher the concentrations we're getting over time, and science needs to keep up to date with what happens as more and more lithium ions are disposed of in landfill. Here's a quick representation of an exam question, 2007, question 20. You were asked, having a look at that cell, you'd need to recognise that it was a car battery. Here they actually give you the equations, but it asks you to identify the anode and write the equation for the overall reaction. Here's my answer. You know that lead is the anode, as can be seen in the first oxidation half, and the overall reaction can be represented as follows. One benefit of car batteries lasting several years, you can't quite see what I've put on the screen there, but essentially, what's the benefit of a car battery lasting several years? Firstly, you would say lead is a bioaccumulative neurotoxin. The fact that car batteries last a long time means that it reduces the likelihood of the buildup of lead in the environment that can cause harm to organisms. So those are the three batteries that you need to examine. You need to know them in detail with regards to their chemistry, their anodic and cathodic reactions, and be able to discuss the cost, practicality, and environmental and societal advantages of the cells.